So, hey guys, hello, good afternoon. So, Vishal here. Okay, so if you remember in the last class, oh, excuse me. Okay. So, in the last class, if you remember, we were discussing atomic structure, right? Do you remember, guys? I hope you remember that, right? Yeah. So, what we do today is that we'll be solving a few questions from the chapter, and we will try to solve advanced questions because once you are good with the advanced level, it will be very easy for you to solve the base level questions, right? Okay. So, I can see a lot of students today. Hi, hello, Shivani, Aditi, Swati, Vaishnavi, Bhumika, Dhara, Dhara. Hi, hello, Dr. Everyone. Okay. So I'm sorry because this is a continued class, but if it feels very new to you, fine. Like you try to recall as much as possible. Okay. But I'll try to make it simple. I'll try to make it as simple as possible. Okay. Yeah. So we will try to have fun along the way because all the questions what we have now they're really simple and you might like it too. I believe so. Okay, good, good. So if you have any doubts, you can text me. So as a text in the chat box right now, so you can text me along the way, right? Okay, so everything will be sorted out. No worries. Okay. So to again tell you that this is a continuation class of atomic structure. So in the previous class we have discussed. So what is an atom? What are the different models of an atom? Right. One is Rutherford model, Niels Bohr's model, quantumic model. So we have seen different models of atom. And we have also derived the expression for velocity, radius, and energy of an atom. So of an electron inside an atom, we have done that also. Okay. So today as a third part, continued part, we'll be solving questions on it. Solving questions on it. Simple, right? Okay. So we'll begin with the first question. Begin the first question. Okay. And this question is pretty simple, though it was asked in advanced class, advanced exam. It was very simple. Okay. So the question is an accident in a nuclear laboratory. So there's a nuclear laboratory, okay, and there is an accident in the nuclear laboratory, resulted in disposition of a certain amount of radioactive material. So from this laboratory, some radioactive material has come out. And it's very dangerous, right? Radioactive materials are very dangerous. So it has come out of the laboratory, okay. And this material has a half-life of 18 days. So what is meant by half-life? Do you remember, guys? So according to the concept of half-life, for example, if you have 100 atoms of nuclear radioactive material, for that to become 50 days, how much time it takes is called as half-life, T half. So from 100 to 50, it's getting half, right? That's called as T half. From 50 to 25, again it is going to take one more half-life, T half. From 25 to 12.5, one more half-life, one more T half. It's simple as that. Okay, the amount of time taken to reduce its initial quantity by half is called as half-life. Simple, right? Okay. So what's next then? Okay, cool. Tests revealed that the radiation was 64 times more than that of permissible level. So initially, if you want to stay comfortably in the room, the radiation will be taken as R naught. But now what I have 64 times more than. So this is very good. This is good for me to stay in the room. But I have 64 times of R naught. Like it's very bad to stay in that room because there is a lot of radiation. That radiation can ionize your particles and it cause mutation in your DNA and that will be very dangerous, right? So no, that's not good. So I currently have 64 times of the permissible level, okay, for the same operation. Now, okay, what is the minimum number of days after which the laboratory can be considered safe for use? Okay, so today the accident has happened. So from now, after how many days is it safe for me to go to the lab? What do you think? So option A is 64 days, option B 90 days, option C 108 days, option D is 120 days. So which is the most good amount of duration for me to enter the lab without any problem? Okay. So students, can I know you from which school you are? All of you, because I'm seeing you all of you for the first time, right? Right? Can I know from which school you are? Okay. cool. Let me know. Okay, the type from which school you are and let me know. Yeah, I know you're all from JME. I was asking JME, which JME? Okay, it's okay. Sure. Okay, cool. So any thought on this problem, guys? So we have two. Let me give you what is given. Acha, Kendriya Vidyalaya. Good. Okay. So I'll try to give you the clue here. Okay. The first clue is that it is given half day. T half time taken for required to become half is 18 days. So that's one quantity which is already given. Second parameter which is given is the permissible level is R naught, and we have currently 64 times of R naught. It's 64 times dangerous now. Okay, so if I go from 64 R naught to R naught, then it's permissible. I can stay in this condition in this room. I can stay without any problem, right? So how do I go from 64 to R naught? So usually after 18 days, this will become half. After 64, it will take 18 days to become 32. Are you trying to get it? Are you trying to get? Okay, cool. So from 32 to 16 to become its half the original quantity is again going to take 18 days. From 16 to 8, 18 days. And from 8 to 4, half of it again takes 18 days. From 4 to 2, it takes 18 days. And from 2 to 1, it takes one more 18 days. So how many 18 days are there totally? 1, 2, 3, 4, 5, 6. So totally 6 times of 18 days, which is equal to 108. So after 108 days, I can go to the room because 64 R naught will become just an R naught, 1 times R naught. So it's very safe for me to go to that particular room. Are you getting what I'm trying to say, students? If you have understood, type yes. If you need some more clarification, you can ask me. Okay, so be comfortable. If you're not with any point, please put it in the chat box. I'll be here to clear it out. Okay, great. So or like mathematically also we can do this. Okay, so it's not tough. So let me tell you. Okay, so how do T half work is that 64 can be written as 2 to the power of 6. Do you get this is simple, right? If you multiply 2 6 times by itself, or if you take 2 to the power of 6, you get 64. That means the quantity to double itself, it is taking 6 times. Similarly, if you divide it by 6 times, you are going to get 64. So this is the number 6, how you get it here. Okay, so this is a shortcut, very simple. Shortcut, how can you find? How many octaves are there? Because it's a very huge number, then you can't do, right? You can't divide by 2 for a long term. So you take it as a power of 2 and it will be very easy for you to solve. Okay. So let me repeat again. So initially there are 64 times the permissible quantity of radiation. For every 18 days it's going to become half. And for it to become 1, which is permissible limit, it's going to take 108 days. Right? Am I clear, students? Respond in chat box. Am I clear? Or waiting for your response, guys. Okay. Okay, then fine. So shall we move on with the next question? Okay, we'll move on with the next question. So the next question is: a metal surface is illuminated by two different lights of wavelength 248 nanometer and 310 nanometer. Okay, and the next thing is the maximum speed of photoelectrons correspond to this wavelength, which are u1 and u2. So these are the velocities. Okay. If the ratio of velocity u1 and u2 are 2 is to 1 and hc is a constant number which is 240 electron volt, the work function of the metal is nearly. So you want to find the work function. Okay. Okay, Mani, Aditi, Deven, Good, good. Responding. That's better. Okay. So let me tell you what's a photoelectric effect in a simple way. So I have a metal here. Okay, I have a random metal. Take for example sodium or silicon, something like that. And now on this metal, whenever a strong light falls on this metal, so this is a photon, we call it as a photon. So when photon falls on the metal, okay, it can eject some electrons. So in this metal there will be atom, there will be electrons revolving around the atom. So this photon might fall on this electron, and this electron might come out. And this whole process called as photoelectric effect. This whole process called as, see, photons say electricity is coming, right? So photoelectric effect. This is what we call it as photoelectric effect. And Einstein gives an equation, okay, which is very simple. He tells us that if this photon has energy E, okay, this photon, like every photon will have its own energy, and this photon has some energy E. Okay, that energy will be used to remove the electron. Okay, so first thing what has to happen? The electron has to come out of this metal. So I'll put phi. So the energy of the photon is used to remove the electron, plus the extra energy will be used for this electron to move with a higher velocity, plus kinetic energy of electron. So this is the Einstein's photoelectric effect. And for this simple equation, he did get a Nobel Prize in the year 1922. He published the paper in 1905, and he got Nobel Prize in 1922 for this simple equation. Okay, so let me tell you once again, the energy of this photon will be used to remove the electron this term, and the remaining energy of this photon will be used for the kinetic energy of electron. So this was what Einstein told. Okay, so let us use this equation and try to understand the question here. So in this question, we have two situations. So let me take the first situation, metal plate situation number 1, and metal plate situation number 2. So in the first case, we have a photon of 248 nanometer falling on the plate, and in the second case, we have we have a light of how much? 310 nanometer. Sorry, it's not visible, I suppose. 310 nanometer falling on the plate. Okay. So now what will happen? An electron will be ejected from this plate, and an electron will be ejected from this plate. Since the colors are different, since the light is different, since the energy of light is different, the kinetic energy of the electron also will be different. So we need to find, they are giving the ratio of velocities, and we need to find the work function. How much energy will it take to remove the electron? So let us let us write the equation, which is very simple. So in the first case, energy in the first case 1 will be equal to work function phi plus kinetic energy in the case 1. Okay, this is the equation I'm rewriting as it is in the first case. Similarly, I'll do it for the second case. The energy of the blue light E2 is equal to, it will be used to remove the electron phi, plus it will be used to increase the kinetic energy of the circle, and in the second case it is K2. You might ask me, sir, why you are not writing phi 1 and phi 2 rather than you are writing phi in both the cases? Because phi is a constant. It depends only on the metal. It's a constant value. It doesn't depend on any other criteria. Phi always depends on the material. Since I'm using the same metal plate, phi will be same. Okay, phi will be same. So they have given information about velocity, and they want us to find what is this work function phi. So we can do that. It's not a problem. How to do this is very simple. Or what I'm going to do now is E1 minus phi is equal to K1, right? I'm rewriting the first equation. Second equation also I'll rewrite it. E2 minus phi is equal to K2. So this is how I'm going to write. And kinetic energy 1 will be written as half mv1 square. Okay, and kinetic energy 2 will be written as half mv2 square. Sorted. Okay, so now if I divide these two equations, I get the answer very easily without any problem. But I have to do a bit of some more calculation here. Okay, so let me do that calculation. I don't know what is phi, but I know what is E1. So E1, energy of photon is given as h nu, or E can be written as E is equal to h nu, or you can write E is equal to hc by lambda. hc by lambda. And hc is given already here in the question. hc is 1240. HCl right here, or it can be written as 1240 by lambda. It's like I can do this. This is one general formula, students. This is a shortcut. So try to remember this. Okay. So what I'm going to do next is I'm going to find E1. E1 is equal to 1240 divided by lambda 1. So what is lambda 1? 248 nanometer. So I'll put 248 nanometer. 248. So how much is this? This is exactly 5. So if you want to check, yes, it's 5 electron. It's 5 electron. Similarly, I'll try to find E2. How much is E2? Uh, 1 Hc by lambda. So lambda in second case is 310. Oh, sorry. Let's divide it. Almost I get this. 1240 divided by 258. It's 5. Great. Okay. And this becomes 4 electron divided by 310. Yes, this is 4 electron. So this photon here, this carries an energy of 5 electron volt, and this photon here carries an energy of 4 electron volt. Oh yeah. So now what I'll do, I'll put this E1 as 5 and I'll put this E2 as 4. And now what I'm going to do is I'm going to divide the both equations. I'm going to divide this equation by this equation because I can do any mathematical manipulations in physics as completely fine. So when I divide equation 1 by equation 2, half and half get cancelled, mass and mass get cancelled. Sort it out. So I can now rewrite this whole equation as in a simple way 5 minus 5 divided by 4 minus 5 is equal to V1 by V2 whole square. V1 by V2 whole square. And I've given that V1 by V2 is 2 is to 1. So V1 by V2 is given as 2 is to 1. So what is 2 is to 1? 2 is to 1, 2 by 1 is 1. Sorry, 2 by 1 is 2. 2 square is 4. So this whole equation can be done as 4. I believe we can solve this now. Very simple, right? So let us solve this equation very simple, which is let me take a different color. It is appropriate for here. 5 minus 5 is equal to 4 into 4 minus 5. I'm going to take this to the right hand side here. So 5 minus 5 is equal to 16 minus 4 5. So what I can do? I can bring this 4 5 here. It becomes 3 5, and if this becomes 11, or 5 is equal to 11 by 3. 11 by 3 is 3.7. Simple as that. Simple as that. Okay, I hope I'm clear. And let me tell you once more. Okay, if students, if you feel difficulty or if you don't remember the concepts, let me know. Okay, I'll explain it again. We will spend some more time on the theory also because most of us learning for the first time, right? It's completely fine. I understand. If you don't get the concept, ask me what is the concept. I'll explain. Okay. So let me explain completely. So there was one photon of 248 nanometer falling on the plate, and there was one more photon of 310 nanometer falling on the plate. Nanometer of the nearest meter. So nanometer. And what is the energy of this photon? I can use the formula which is E is equal to h nu or E is equal to hc by lambda. H is constant because then I can write 1240 by lambda. Lambda should be always in nanometer here. So this is 248 nanometers. I'll put 248 nanometer here. When I divide this, I get E is equal to 5 electron volt. So the energy of this photon is 5 electron volt simply. And similarly here, energy is equal to 1240 by 310. 3 ones are 4. So 4 electron volt is the energy of this photon. So this photon has energy of 4 electron volt. Simple. Okay. So now let us write the Einstein's equation, which is as simple. Okay, which is energy. So I'll write it here. Energy of photon will be used to remove the electron plus kinetic energy. So for this case, phi is the energy of electron. Sorry, phi is the energy of photon plus its some amount of work will be used to remove the electron. Phi plus kinetic energy, which is half m v1 square. And here, what is the energy of photon 4? And it will be used to remove the electron plus the remaining will be used as kinetic energy half m to v2 square. Or let me rewrite this equation as phi minus phi is equal to half m v1 square, and let me write this as 4 minus phi is equal to half m v2 square. Divide equation number 1 by equation number 2. So let us do that here. Okay, yeah. So phi minus phi divided by 4 minus phi, left hand side divided by the right hand side, half m v1 square by half m v2 square. So half m can be cancelled from both the sides, and v1 square by v2 square can be written as v1 by v2 whole square. And in the question it was given as v1 by v is to 2 is to 1. Again, whole of this becomes 4. Solving this as 5 minus 5 is equal to 16 minus 4 5. I'll bring minus 4 5 this side. It comes plus 4 5 minus 5 is 3 5. is equal to 11, or phi is equal to 11 by 3 or 3.7 electron volts. This is the answer. Even though it was an advanced question, it's pretty simple, right? So if you know the concept, you can solve it very fast. You can do it very quickly, very easily if you know the concepts clearly, right? Okay. Okay, students, am I clear? So am I clear with the question? So option A is the right answer for this advanced question to ask the A to 14. So when you are very good at these kind of tough questions, so what will happen is mains and lead becomes very easy for you. You could score very well in your exams without any hassle. Okay. So let me know if you are clear, and let me know if you need me to explain it again. Okay. Okay. Cool. So and next we are going to study about we spend some 5 to 10 minutes on the theory of X-rays. Okay. So let us try to understand how are X-rays created. So you might have gone when you're playing when you're a kid, you might have broken your finger or you might have broken your hand, or some of your friends have broken their bones, right? So then you might have noticed we go to doctors and take the X-ray. Okay, and in X-ray we can see structure of our bone, but not our muscles. Okay, so I'll tell you why it happens, why we use X-ray later. But now I want you to tell me how can I extract X-ray? How can I create X-ray? Because X-rays are only available in the hospital, that in a particular room, only in a particular machine, right? So how does that machine can create X-ray? Is my question. Okay. So what's the physics behind it? So can I create any ray? Can I create therefore alpha, beta, gamma rays, ultraviolet rays, infrared rays? If I can create X-rays, I can create any rays, right? So then how do I do that? Okay. So let me get broken eye. Yeah, of course, right? Even I while playing football, I do have broken my toe finger. Okay. Okay, cool. So coming back to the concept here, X-rays. So there are usually two ways to get an to produce an X-ray. Okay, so let me tell you one basic concept which is very simple. So if you take a charged particle Q and if you keep it at rest, for example, plus 3 coulomb, if it is not moving, if it is at rest always, then what will happen is this 3 coulomb will give us electric field. I hope you remember electrostatics. Charge is at rest, gives only electric field. Gives only electric field. As simple as that. Okay. So my next concept will be what if I take this charged particle and what if I move with constant velocity? If the velocity is constant, then what will happen? So I'm taking this charged particle 3 coulomb and I'm moving this certain velocity. I'm moving this charged particle with certain velocity v. So when charge moves, the rate of change of charge is nothing but current, right? So charge moving is nothing but current. So what will happen when there is current? If you remember magnetic field, we know that whenever charges move, electric field as well as magnetic field is created around the coil. So now when the charge moves, so let me summarize here. When the charge is at rest, I get only electric field. When the charge is moving at constant velocity, I get electric field as well as magnetic field. You can notice, right? Our right hand screw Faraday's experiments. So we get electric field as well as magnetic field. But there is one more very important concept, which is whenever this was the first condition, this was the second condition, and the third condition is whenever this charged particle accelerate, whenever its velocity is not constant, but it either decreases its velocity or if it increases its velocity. So whenever there is acceleration, okay. Good afternoon, Narco students. Hello, hi. So and whenever this charged particle is accelerating, so we get all kinds of things. So one is there is a charge, so there is electric field. It is moving, so there is magnetic field. And since it is accelerating, it is going to emit a photon. It's going to emit radiation. It's going to emit radiation also. So students, let me finalize now. If a charged particle is at rest, if it is not moving under the conditions of electrostatics, we get only electric field. We get only electric field. If a charged particle for a 3 coulomb, 5 coulomb, or minus 3 coulomb, minus 10 coulomb, if that number of charged particles are moving at constant velocity, then I get electric field as well as magnetic field. But with the same charge, is accelerating or decelerating, anything is fine, accelerating or decelerating, then I get electric field, magnetic field, as well as this charged particle will emit radiation. Will emit radiation. Okay. So same concept we can use to create X-ray. Okay. So I have our nucleus here. Okay, guys. Nucleus is positive charge because it has protons and neutrons. Neutrons are neutral in charge. So in this nucleus, I have positive charges. I'll keep a positive target nuclei. Okay, that is a random nucleus. So keep it at some point. Now I'm going to take a fast moving electron. This electron is moving very fast. It has a lot of kinetic energy. Okay. So this is moving very fast towards right side. But as soon as it comes near the nucleus is positive, electron is negative. So it try to attract. So this nucleus will try to attract. If the electron is very slow, they'll again touch each other. But since this electron is moving very fast, this is slightly deviate. Initially, it was supposed to go in this straight line, right? And supposed to go in this direction. But now, due to the attraction, due to the Coulombic force, it is moving towards right, right? And if you notice, there is a curve here. There is a curve, small curve here, right? So curve means it's a circle. So whenever an object is moving in circle, there is centripetal acceleration. Fc which is equal to mv square by r is centripetal force, and centripetal acceleration A is equal to v square by r. So here, this fast moving electron goes towards its positive nuclei. It attracts a bit and it deviates the path. It curves. Okay, it curves a little. So whenever a particle is moving along a curve, there is centripetal acceleration. So therefore, this charged particle is accelerating centripetally. It is accelerating. And as I told you from the last concept, whenever there is some kind of acceleration for a charged particle, it's going to emit radiation. And since this particle is also moving in curve, it's going to emit X-ray. Since it's having high velocity, it's going to emit a very strong photon. And that strong photon is X-ray. So this is first way of getting X-ray. And these kind of X-rays are called as continuous X-rays. Continuous X-rays. Am I clear? So the first way to create X-ray is simple. You have positive nuclei and you make a very fast moving electron pass close to the nuclei, it bends. Whenever it's bending along the path, it's going to emit radiation because it's a centripetal acceleration. So it will bend whenever whenever it bends or whenever it curves, it's moving in centripetal force, then it's going to emit a very strong radiation called X-ray. And if this X-ray passes through your hand and it falls on the screen, you can get the image of your hand. That is how simple getting an X-ray image is. Okay, that is one way of creating X-ray. And we have one more kind of X-ray and one more method of creating X-ray, which is called as characteristic X-ray. Okay, so you might already know this concept. Okay, so let me write the ground state of hydrogen N is equal to 1, and the first excited state N is equal to 2. Well, let me write it a bit higher. N is equal to 2, and next excited state N is equal to 3. Next orbital principal quantum numbers, these are principal quantum numbers. N is equal to 4. Next N is equal to 5. Next N is equal to 6. Next N is equal to 7. So these are all different orbitals or stationary states of hydrogen. And we already know that whenever an electron jumps from higher orbit to lower orbit, it's going to give out photons. It's going to give out photon, right? And this photon will have energy. It's equal to the different levels. For example, here in the ground state, we know that the energy of the ground state is minus 13.6 electron volt, and energy in the third state is minus 1.51 electron volt, and here it is minus 3.4 electron volts, and here it is minus 0.8 electron volt. See, whenever it jumps from N3 orbit to N1 orbit, what is the difference in their energy level? Here it is minus 13.6, okay, and here it is minus 1.5. What's the difference between these two? If I take the subtraction, I get 12.1. So 12.1 amount of energy will be released. Okay, so here it was minus 1.51 energy. Here it should be minus 13.6. That means it has to lose some energy in the form of photon. So this is a photon which I'm getting at 12 electron volts. This much amount of energy is emitted. And if it jumps from higher orbit, I get much more energy. So this is like 12 electron volt is nothing but it's almost closer to X-ray. If you take an higher orbit, like seventh orbit, and from seventh orbit, if you make it to fall on the first orbit, it's going to emit much more stronger radiation, and that radiation is nothing but X-ray. So you can see in the diagram. So let me zoom it here. Okay. Give me a second. So you can notice in the diagram, there was a free electron here. It was a silicon atom. Okay, yes, side. So we have taken silicon atom, and there was a free electron. So this free electron uh, then jumps from the free state to the first ground state. Okay, it's jumping from free state to ground state, and when it jumps, it's going to emit photon. And this photon is very strong because it has 12 electron volt of amount of energy, or it might have 13.6 amount of energy. And this strong photons we are getting outside is nothing but X-ray. It's nothing but X-ray. Okay. And we get different kinds of X-ray from one orbit to one orbit. Different energy is there, right? So for every orbit, we get different kind of X-rays. Am I clear? Okay, so let me summarize all of this here, and we'll start solving the problems on X-rays. X-rays is a very important concept, and if you want to study the theory, I believe all of you know H.C. Verma, concept of physics H.C. Verma. This is very small chapter. It's almost 5 to 6 pages just on X-rays. It's very simple and very easy. Try to go through that. But okay, let me summarize. So there are two kinds of X-ray. One is continuous X-ray, continuous X-rays. So how do I get these X-rays? Uh, I get these X-rays when I take a positive charge, positive nuclei, okay, and after this positive nuclei, if I send an electron, okay, if I send an electron here, with a very fast, very high velocity, this will be attracted. It is supposed to go in straight line now. If there is no nuclei, because there is this nuclei, now this is going to bend slightly towards the positive, then it will go in a straight line. And since it is curving here, it's moving in circle, there will be a centripetal acceleration, and therefore it's going to emit radiation. Because whenever charges will accelerate, it will emit radiation, and this radiation is called as X-ray. Very simple. So this is one way of getting X-ray. And we have second way. Second way is characteristic. Bro, RN, I'm trying to teach the advanced concept. So X-rays is taking syllabus for advanced and means to. Okay. Characteristics. It's not. I don't think it is not there for CBSE, but it's there for advanced. It will help you. Okay. So go through it. So how do I get characteristic X-ray? It's very simple. We know something called a spontaneous emission. So I'm writing different orbits of hydrogen atom. Okay. So when an electron, so let me take an electron. So when an electron, negative electron, jump from one orbit to higher energy orbit to lower energy orbit, it's going to emit photon. It's going to emit photon. And this photon is nothing but X-ray. A high energy photon is X-ray. Okay. So why it is called as continuous is because it can take any values. Okay, it depends on the velocity and it depends on the curvature. It can take any values, but it's called as characteristics because it can only take specific values. From here to here, it will take a known amount of value. From here to here, we can calculate how much value it is going to take. If it jump from here to here, again, it's going to emit some photon. We can calculate how much is that photon. We know this value of this every step emission. Okay, but we cannot find this is both X-ray because it can have any amount of velocity. So this X-ray can take any amount of energy. But here, since the orbitals are fixed, the energies are also fixed here. That is why they are called as characteristic X-rays. Impact parameter. I do have a problem on impact parameter RN. Okay, so I'll come back to that at the last. I do have a problem on it. Okay, great. And we have given names also, students, because it's very good to give names instead of telling random X-rays. We have given names for them. Okay, which is, so let me do that again. N1, N2, okay, N3, and N4. Okay. So whenever an electron jumps from higher orbit, for example, if it is jumping from second orbit to first orbit, okay, it is called as K alpha. It is called as K alpha. Whenever it jumps from second orbit, from the third orbit to the second orbit, it's called as K beta. K beta. And whenever it jumps from the fourth orbit to the next orbit, it's called as K gamma. So these are the different names which are given. There is no need for you to remember all of this, but just remember that you can have different kinds of X-rays and they are given different names. Because this orbit is also called as K, This is called as L, this is called as M, this is called as N. So the first is K alpha, the second is K beta, the third is K gamma. Then we can go right, you can go higher and higher on the problem. And last we have one more thing. So if an electron jump from this orbit to this orbit, since it's coming to the L shell, I can call this as L alpha. And if it jump from next higher orbit, I'll call it as L gamma, sorry, L beta. Next, if it jump from much more higher orbit, then I'll call it as L gamma. So I can give different names. It's completely fine. Okay. So, but for your JEE syllabus and NEET syllabus, we usually concern with only K alpha. But we only try to use K alpha as much as possible. Okay. Okay. And one more thing. So there is one more extra concept. Okay. Radhika, Lyman series. Yes, yes, Radhika. I'll come back to Lyman series very soon. Okay. So this is not exactly Lyman series. Yeah, we do call this series as Lyman series, next Palmer, next Passion. I'll come back to that very soon. Okay. Give me a second. And okay, so we usually consider with K alpha. What is K alpha? The emission of X-ray when an electron jumps from second orbit to the first orbit of hydrogen is called as K alpha simple. And there was a scientist called Mosellis. Okay, Mosellis, and he gave us a law. He gave us that the frequency of this X-ray, I mean, X-ray is coming out right in the form of photon. So this frequency under root is proportional to some constant A z minus 1 for alpha lines. For alpha lines, this is the formula. It's an empirical formula. We can't derive this formula. We have to do the experiment and then find it. So that's why it's called as empirical formula. So according to this formula, let me explain what this formula tells us. It tells us that the frequency of this photon has some frequency, right? The frequency under root is proportional to constant A into Z. Can anyone of you tell me what is Z from last class if you remember? Do you remember, Radhika? What is Z? Okay. Okay. So Z is atomic number. Z is atomic number. Z is atomic number. Okay, and one is constant. So this is how the frequency of an X-ray depends on. It depends on the atomic number. It depends on the nucleus. If this nucleus is very big, if it has lot of protons, attraction will be very high. If it has less number of protons, attraction will be very low. So therefore, it depends on the atomic number also. Okay, very simple. So let me summarize the whole thing. There are two types of X-ray: continuous and characteristic X-ray, and right. Okay, I'll tell you that. So according to the Moseley, he did a small experiment and he gave us one law which is root of frequency is equal to A times A is a constant number. Okay, don't worry about constant. Z minus 1. Okay, where mu is the frequency of the photon, Z is the atomic number, so atomic mass, right? No, atomic number. So it is atomic number. Okay, so this is what he gave us the formula, and D is constant. It's a constant number. So we can manipulate this formula in any ways. So we can convert from frequency to wavelength. It's very simple. Squaring on both sides, I get under root frequency squared is equal to a square z minus 1 square. I'm squaring it. Square and square root get cancelled out. I get frequency is equal to a square z minus 1 whole square. And either that C is equal to f lambda or C is equal to nu lambda or C by lambda is equal to nu. So instead of nu, I can write C by lambda, which is equal to a square into z minus 1 whole square. Okay, so C I can bring it down. Therefore, 1 by lambda is equal to a square by C into z minus 1 square. Or I can write 1 by lambda is proportional to z minus 1 whole square. See, I can manipulate it. I can manipulate it in any number of ways. It depends on the question and the person who's going to ask the question. As they can manipulate it in any different way. Okay, so let me tell you what was happening here. Okay, so there was Moseley's law, which was root of frequency is equal to e to z minus 1. Simple. Oh yeah. And let me take the square root and put it to the right hand side, it becomes square. So a square ho gaya and z minus 1 square in the right hand side. And C is equal to f lambda. This is a very simple thing which we will learn from 11th. So remember that. And I can find out that C by lambda is equal to nu. So C by lambda is equal to nu, done, is equal to a square minus z minus 1 whole square. Bring C to the denominator, 1 by lambda is equal to a square minus c and z minus 1 whole square. A and c are constant. C is speed of light, a is constant. So I can remove both of them and I can say 1 by lambda is proportional to z minus 1 whole square. So yeah, with that formula we can solve the question. It is asking you to put j and mass. Okay. So let me read the question and let me clarify it to you. I'll solve this question and I want you to solve this question. Okay. Right. Both of them are very similar. So let me explain. The wavelength of a copper. So we are using copper material and we got an X-ray and that X-ray has a wavelength of lambda. Okay. So the lambda is the wavelength of k alpha X-ray of copper. Copper is an atomic number of 29. And lambda MO is the wavelength of K alpha light of molybdenum. Okay, so this is one more kind of material and it has an atomic number of 42. What is the ratio of lambda of copper by lambda of molybdenum? So if you remember guys, according to our Moseley's law, root of frequency is equal to a into z minus 1. Taking square on both the sides, I get frequency is equal to a square into z minus 1 whole square, or c by lambda is equal to a square into z minus 1 whole square, or I'll bring the c to the denominator. So this is the uh, expression which I know, right? So let us first write this expression for copper, for Cu. So 1 by lambda of copper will be equal to a square is constant, c is constant, keep it as it is, no change. And z of copper minus 1 whole square. Simple. So I written the first equation for copper. So we'll do the same thing for molybdenum, which is uh, MO. MO is the what is this? Element. Like I can't tell the name. Fine, fine. Okay, so 1 by lambda MO is equal to a square by c is constant. And what is it? Z of molybdenum minus 1 whole square. So this is equation number 1, this is equation number 2. Divide both of them. Just solve it. The question is simple. So dividing both of them, 1 by lambda of copper divided by 1 by lambda of molybdenum is equal to a square by c cancel हो गया because it's a constant. I'm left with z of copper minus 1 whole square divided by z of molybdenum minus 1 whole square. And the denominator goes to numerator. It becomes lambda of molybdenum here. So it becomes lambda of molybdenum by lambda of copper is equal to z minus 1 copper whole square and z minus 1 whole square. Okay, we will solve this. What is z of copper? It's given the question. Z of copper is 29 minus 1 square. Okay, divided by what is the z of molybdenum? Molybdenum is a number of 42. So 42 minus 1 whole square. So this is 28 square by this is how much? Sorry, yeah, 28 square by 41 whole square. So we need calculator now. So let us. Is a multiple of 3. No, it's not a multiple of 3. So let me do it manually. So here they're asking me lambda of copper by lambda of molybdenum, right? So let me shift it. Let me take the reciprocal. So therefore lambda of copper by lambda of molybdenum. I'm reversing both the upper and denominator and numerator. It becomes 41 by 28 square. So what is 41 divided by 28? It is 1.6. So what is 1.64 into 1.64? Yeah. So it is almost option B. It's almost option B, right? Yeah. So this is how you do it, students. It's very simple. So I'll show you two once again. So pay attention. Okay. So which is 1 by lambda, we can solve it in this way. 1 by lambda is proportional to z minus 1 square. Very simple. Therefore, 1 by lambda of copper is equal to copper is 29 minus 1 square proportional to, and lambda of molybdenum is proportional to 42 minus 1 whole square. So this is how I do it. Okay, dividing both of this, numerator of numerator goes to, okay, 2.3, right? Numerator of numerator goes to the above, denominator of denominator goes to numerator, so it becomes lambda of molybdenum the lambda of copper is equal to 28 by 41 whole square, or I can rewrite this as lambda of copper by lambda of molybdenum is equal to 41 by 28 square, and when you solve it, you get approximately 206. Okay, and it is now I think let us 2.14. It is problem. Okay, am I clear, students? Was it boring? All right. I hope I'm clear. Okay. 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 So moving on to the next question is exactly similar. Exactly similar. To try to solve this, I'll give you 2 minutes. I'll give you 2 minutes. It's 3:46 now. I'll wait for 3:48. So try to solve this. I'll explain you the question. It was asking to identify advance. Okay. The K alpha wavelength emitted by an atom of atomic number Z11 was lambda. Okay. So again, we'll write our master equation, which is 1 by lambda is proportional to Z minus 1 whole square. Okay. For atomic number of 11, we get an wavelength of lambda. Okay. So then find the atomic number. So we have to find this atomic number unknown, which is giving us 4 times the lambda. If you get a 4 times weaker X-ray, what should be the atomic number? They're asking what is the atomic number for the weaker X-ray? Is the question. Okay, sir. Try it out. Try it out. Come on, guys, work it out. So if you just use the equation now, you'll be able to get the answer without any problem. Okay. Okay, hello, hi. So don't worry, you have joined the class a bit late. Don't worry, you can watch it from the beginning. Okay. So no worry. And so if you all guys are coming again tomorrow, right? So I'll study this chapter, so you can follow the issues. So it will be easy for us to understand and solve the problems too. Okay. So times of let me solve it out. So this is our the equation which we derived just a few minutes ago. And okay, so how to solve this? Let me take it as in a very simple way. For the first element, I take 1 by lambda 1 is proportional to Z1 minus 1 whole square. And for the second element, let me take it correct actually. Good, good. Okay. So next what I do is I take the second formula, which is 1 by lambda 2 is proportional to Z2 minus 1 whole square. Very simple. So I have two equations. And since there is proportionality constant, so I have to divide. So that will be better. So now while dividing, what will happen is simple. 1 by lambda 1 divided by 1 by lambda 2 is equal to Z1 minus 1 whole square divided by Z2 minus 1 whole square. So this is how it looks. But denominator goes to numerator. So I can write this as lambda 2 by lambda 1. Simple. And Z1 I have known. Z1 is given as 11 in the question. And lambda 2 is 4 times lambda. Lambda 1 is just lambda. So lambda get cancels out. So left is 4. This whole equation is equal to 4. Okay. So 11 minus 1 is 10 and 10 square is 100. 10 square is 100. So let me slightly rearrange this a bit. Okay. Correct, Aditi. Good, good. So this becomes 100 by 4 is equal to Z2 minus 1 whole square. So what is 100 by 4? 100 by 4 is 25. Sorted. Okay. So let me take under root both the sides. Square and square root cancel. Root of 25 is 5. Z minus 2 minus 1 is equal to 5, or 5 plus 1 is equal to Z2 is equal to 6. Okay, so you got 4 marks in advance. You have to be happy. Right? So it's pretty simple. So try to remember what I've written here, right? The Mosell's law and the different kinds of X-rays what they have given. So let this is 1 by lambda is equal to a square by c to z minus 1 whole square. So try to remember these two formula. If you want, take a screenshot, or the video will be available in the channel all the time. So you can come back and note if you want to remember it, you can remember anytime. That's completely fine, right? Z is equal to 6 means carbon. Of course, sorry. That is 6 is carbon, right? That's right. Okay, cool. So great, awesome. So now shall we move on to the next question? Which shall I select? Mm, yeah, this question is good. This question is good. We'll go with this question. Okay, because this requires a bit of thinking, but it's very easy. There is no need for you to use pen and paper. If you know the concept, you can answer it very quickly. Don't worry, these are all the questions. But I've selected this for now. A beam of electrons is used in Young's double slit experiment. The slit width is d. When the velocity of electron is increased, then, so very simple. If you know Young's double slit experiment, what happens? We have two slits, slit S1 and slit S2. Usually what happens, the light enters from slit S1, light also enters from slit S2. Both of them will meet and they undergo interference in the center. They interfere with each other, right? And they're going to create a interference pattern. So at the center there will be a bright fringe, then a dark fringe, then a dark fringe again here, then a bright, then dark here, then dark here. So we get this kind of fringe pattern in the experiment, right? I hope you remember. Right. Good. So now what happens? What is happening here is instead of using light waves, instead of using light waves here, I'm going to use electrons. So it's really awesome. Even if you use electrons also gives interference pattern. Okay. So now I'm using electrons, and whenever you use electrons instead of light waves, we get interference pattern. You might ask me, sir, why, sir? This is a bit, so am I right, sir? Like, does this happen? You might ask me. I see exactly. It happens all the time because if you know de Broglie's wavelength, which is lambda is equal to h by p. So this de Broglie's equation tells us that okay, any particle which has momentum is a wave. Any particle which is a wave has a momentum. So it's called dual nature. I hope you remember dual nature of light. Similarly, electron also has dual nature. It can behave like wave or also it can behave like particle. Now in this situation, electron itself is behaving like wave. And when I use wave, this electron, it also gives me interference pattern. And options are no interference pattern is observed. No, this is not true because we get interference pattern. Fringe width increases, fringe width remains constant, fringe width decreases. So those are the three options. So all of them are asking about fringe width, and we know that fringe width is equal to lambda capital D by small d. So this is the formula for fringe width. So let me write it down here. Okay. So physically, what I'm trying to do is I'm just changing the velocity of electron. I'm not changing the distance. I'm not changing the slit width. I'm only trying to change the velocity. So here, according to dual nature, we can write that momentum as mass into velocity. Lambda is equal to h by p or lambda is equal to h by mp. So what will happen now? As I increase the velocity of electron, which is in the denominator, lambda decreases. Am I right? Are you getting my point? So de Broglie gives us this equation, which is the wavelength of any particle is nothing but Planck's constant by mass into velocity or Planck's constant by momentum. Okay. Just a minute. Wave particle oscillation nature. Yes, that's correct. Okay. So now what's happening here is I'm increasing the velocity according to the question. The velocity is increased. What will happen? So if I increase the velocity, lambda decreases. Okay. So if I decrease lambda here, what will happen to fringe width? Come on, tell me. Lambda which is directly proportional to fringe width. As the velocity jab increase hoga, lambda decreases. And when lambda decreases, what will happen to beta? What will happen to fringe width? Come on. So take a guess. B, C, D are the option. They're directly proportional. So lambda decreases, beta also decreases, right? Good. So when lambda decreases, beta also decreases because they're directly proportional. They're directly proportional to each other. So what will happen? The fringe with beta decreases. C is the right option. C is the right option. Correct sentence. Good, good. Okay, am I clear? Radhika, am I clear now? Okay, great, great. Very simple. So velocity, when I velocity lambda decreases, weight also decreases. Sorted out. Okay, good. So again, 4 marks in advanced question, right? So see, I mean, you should be very good with all the concepts, so it will be very easy for you to solve too. And going back to the next question here, for a uranium nuclei, how does it varies with mass? Okay, so sorry. For a uranium nucleus, how does its mass vary with volume? So they're asking if I have uranium nucleus, just 230 around nucleons. There are 92 protons and the remaining around 140 neutrons are available in the uranium nuclei. So they're asking the mass of this nucleus is proportional to volume, or is it inversely proportional to volume, or is it proportional to root of volume, or is it proportional to square of volume? It's a very easy question. Correct. Good, Radhika. That's right. Anybody else from YouTube? What do you think the answer is? Mass is directly proportional to volume, inversely proportional to volume, proportional to v square, proportional to v to the power of half, or root of v. So exactly, we know that density is equal to mass by volume. Simple. Okay. So therefore, I can write mass is equal to density into volume. Right. So can I do this? Can I tell it is directly proportional to volume? Do you require it? Yes? No. This is more than sufficient. So it would easily say that the mass is directly proportional to volume. So I'll give you a small concept also. Okay, which is see hydrogen easier. Okay, and it has only one proton. Okay, so it has some mass of proton EMP. Now, when I increase the size of nucleus by adding one more proton and two more neutrons, so this becomes helium nuclei, and its mass increases by 4 because I'm adding 4 neutrons. Okay, and similarly, if we take lithium has 3 protons. It has 3 protons and it has 3 neutrons. You can notice the mass is increasing as volume increases all the time. So the mass increase over volume also increases drastically. Okay, so you can easily, without any problem or without any confusion, you can see that mass is proportional to volume. Okay, so density is constant, so remove it out, mass is proportional to volume. So such a simple question was asked in 2 and 3, and see, even though I'm really, I'm like, I promise you that if you are very good at basic fundamentals of physics in both and well, you would easily sort it out without any problem at all. Okay, you could all qualify. At least you could get a good rank. You might not be able to get an IIT, but that's possible if you are very good with the concepts. Okay. So let me solve simple questions first, then we go to tough questions. Okay. So one doubt. That V is proportional to I, or okay. So Radhika, what happens is V is equal to IR in Ohm's law. V is proportional to I into R. Or usually we can take V by R is equal to I. The resistance, when you increase the resistance, current will reduce. When you increase the potential, current will increase. So we usually write it as V is equal to I into R. Okay. This is potential is proportional to current. Okay. Good. And coming back to one more question here. Okay. Hello. Hi. Yeah. Now, the electron emitted in beta radiation originates from. Okay, so if you know, students, the radioactivity. So, let me explain you very quickly what is the radioactivity. So, radioactivity is a process where strong nuclei, just like of this uranium. Uranium was a very big nuclei. It's very strong, but it's unstable. So, what this very big nuclei will do to become stable? This is big unstable nuclei. So, this big unstable nuclei will become small stable nuclei by emitting particles. By emitting particles, it becomes. So if it emits an alpha particle, or if it emits an helium nuclei, which has 2 proton and 2 neutron, then it is called as alpha decay. And if this nuclei emits an electron, it is called as beta decay. And this nuclei, it emits a very strong radiation, and if it becomes stable, that is called as gamma decay. So in radioactivity, we have 3 kinds of decay. So we have a very unstable, very big, like uranium or radium, they're very big and they're unstable. So they want to become stable. So how do they become stable? They reduce their size to become stable. So there are three ways of they becoming stable. One is they emit helium nuclei, it's two protons and two neutrons. They come out of the unstable nuclei and it becomes stable. That is called alpha decay. Next one is this very unstable nuclei will emit electron when it becomes beta decay, and this very unstable nuclei will emit gamma particle and become gamma decay. So it becomes it emits radiation and becomes gamma. Now, so they're asking us in the question here. Okay, so okay, Radhika. So now here in the options you can guess now. Okay, the electron emitted in really sorry. The electron emitted in beta radiation originates from the electrons emitted in beta radiation originates from, will they come from inner orbit, or will they come from the free electrons existing in nuclei, or will they come from neutron in the nuclei, or will they come from photon? So you can guess it very easily here. Come on students, give it a try. Give it a try. So I told you the nuclei is going to emit the particles, right? So no, this beta decay doesn't happen in the orbits. No, that's gone. It is not free electron coming. This beta decay is happening from the nuclei. Okay, and if it photon escapes, if a photon escapes from the nuclei, it's called as gamma decay. So that is also not an option. That is also not an option. Correct, Aditi. Good. Okay, so the answer is option C. Decay from neutron in a nuclei. So what happens is one neutron in the nuclei. So how do I get an electron? You might ask me, sir, in nuclei, there is only protons and neutrons. But how can an electron come, sir? Electron will be orbiting outside now, sir. How did I get this electron? You might ask me, but it's very simple. One one neutron in the nuclei will convert itself into a proton and an electron. See, proton has positive charge, electron has negative charge, neutron has zero charge. So positive and negative combine, it becomes zero. So a neutron splits itself into proton and an electron, and this electron will be emitted out, and it is called as beta decay. Am I clear? I hope you're clear with all these 3 points. So the unstable nuclei will become stable by emitting an electron, and that electron comes from the nuclei. The neutron splits into proton and electron, and it becomes um, the electron will be ejected out. The electron will be ejected out of it. Simple, right? Good. Okay. So I hope you're clear. Okay. Moving on to next question. What is the order of magnitude of density of uranium nuclei? So they're asking how dense is uranium nuclei. They don't want you to give the exact answer. They are okay if you give a random particular closest answer. Okay, if you give a closest answer, it's completely fine. Okay. So okay. Guys, keep solving. Radhika, notice here. So this nuclei, now this strong nuclei will become stable by emitting alpha, or by emitting beta, or by emitting gamma particle. So alpha particle is nothing but helium nuclei, beta is nothing but electron, gamma is nothing but a photon. Okay, so how does this emit electron, Radhika? It emits just by, there are lots of neutron and protons in the nuclei. One neutron splits itself into proton and electron. So if you take the mass, this mass will be 1.667 atomic mass unit, and this will be 1.66 atomic mass unit, and this will be 1.0.002 atomic mass unit. See, if you add mass, you get mass conservation. If you add charge, so positive and negative becomes zero. Everything is balanced. So neutron splits itself into proton and electron. So option C. The neutron decays into nuclei, give rise to electron. So that is a source of beta radiation. Okay. Right. Good, great. Okay. So now they want us to find. Okay, good. So now they want us to find the magnitude of density. So I already wrote this formula, which is density is equal to mass by volume. Mass by volume. So we'll use the same formula. What is mass? So if you have a nuclei, so there are lots of protons and neutrons. Protons, neutrons. There'll be a lot of them. So we'll approximate all of them have same mass. Neutron and proton mass are approximately equal.
So mass of every nucleon is mass of equal to mass of proton. I'll put MP. And how many of them are there? There are A types, atomic mass number. Right. For example, we write every element as x to the power of z into A, where A is called atomic number. It gives us the number of protons. Atomic mass number A gives number of protons plus number of neutrons. So total nuclei. A gives the total mass of nuclei. So what I can do here is the total mass of nuclei will be the atomic mass number into mass of individual protons. Okay, so that is how I can write the mass. AMU, that's correct, atomic mass unit. So atomic mass number A multiplied by mass of protons. Because mass of proton and neutrons are equal, I just consider only mass of proton. Okay. Lastly, what is volume? Nucleus is spherical in shape, so I write 4 by 3 pi r cube. Pi r cube. And if you remember the first concept from the chapter of nuclear radii, that it's the radius of nucleus given as r naught, okay, a to the power of 1 by 3, where a is atomic mass number. So this is a formula which you remember. So as the atomic mass number increases, the radius also increases, but they have a factor of 1 by 3. They have a factor of 1 by 3. Okay, so now let me substitute that. Density is equal to atomic mass number into mass of protons. I'll tell you once more why do we get these terms, don't worry. Into 4 by 3, 22 by 7, right? Or I can write it as 3. Approximately I can write it as 3 also, because there are just asking me the order of magnitude, right? Into r cube. What is radius? Radius is r naught a to the power of 1 by 3 whole cube. R cube now, so I have to cube this here. So cube of r naught becomes r cube, and a cube and cube root becomes just a. Just a. So this is how the formula modifies itself into. This is how we get a modified formula. Okay, and you can notice, students, a and a get cancelled out, and all you need to do is a substitution now. So let us do this, and let me cancel 3 and 3 also here. Approximately 3 and 3 also will be get cancelled out. So now we need to remember few constant. Usually it will be given in the first page of the exam. So mass of proton is given in the question itself here, which is 1.67 into 10 to the power of minus 27 kg given already, divided by 4 into r naught is 1.25 into 10 to the power of minus 15, and it is cubed. So I'll put cube here. Okay, so how much is 1.25 into 1.25? 3 times. So let me do that. 1.25 into 1.25 into point 2, oh, 0.25 into 1.25. I get 2 approximately. After cubing 1.5, I get 2 here. Okay, and the 10 to the power of minus 15 cubed, I get 10 to the power of minus 45. Simple, sorted out. Okay, so this 2 ones are 2.8s are, okay, and 4 ones are 40.2s are. 10 to the power of minus 27 is here. 45, if it goes up, it becomes 10 to the power of plus 45. So when you solve this, what will happen? 10 to the power of 27 and 45, you are left with 10 to the power of 18. 10 to the power of 18, and there is 0.2, or you can write this as 2 into 10 to the power of 17. So option B is the right answer. So you can notice how the density of nuclei is humongous. Okay, it's very, very large. So Aditi, I think you just missed by a factor. Okay, so shall I do it again? Shall I do it again? I'll explain the whole thing again. So pay attention, everybody. Okay, just a minute, Radhika. Which is, sir, R naught means it's a constant, Radhika. Okay, it's a constant value. R naught is usually 1.25 into 10 to the power of minus 15 units. Okay, so now let me tell you that density of a nuclei is its mass by volume. Very simple. Okay, so how do I find the mass of the nuclei? There are some number of neutrons, some number of protons scattered all over the nuclei. But now I'll consider all of them as protons because their mass is approximately same. So I'll write all of them as P, P, P. Okay, so all of them as protons. So how many protons do I have? I have A times A number of, for example, if I write uranium 92, 232. So totally how many number of protons or neutrons I have? I have 232 of total constituents. In nucleon, complete nucleon, I have 232 particles. So 232 are the particles into mass of individual particle, MP, right? So usually what we can do is, to find a mass of nucleon, I can write the atomic mass number into mass of individual proton, divided by volume is 4 by 3 pi r cube. R cube is nothing but r naught a to the power of 1 by 3 cube. So sir, why do I do like this? Is because the radius of nuclei are so green and green, they camouflage each other. So let me choose a different color. The radius of nuclei is proportional to the cube root of atomic mass number. So after putting the cube here, and after putting this 3 to that cube here, cube and cube get cancelled, it becomes 1. So A and A get cancelled out. Okay, mass of proton is how much? 1.6 into 10 to the power of minus 27 kg divided by 3 and pi I'll cancel out approximately. I'm only left with 4 here into what is R naught cube. R naught cube is this one cube. This becomes how much? Approximately 2. Okay, 2 times into 10 to the power of minus 15 cube, 10 to the power of minus 45. Okay, so this becomes 8. 4 2s are 8, 8 1s are 8.2s are. Okay, so our left with is 0.2 into 10 to the power of minus plus 45, minus 45 goes to numerator, becomes plus 45, plus 45, 18. It becomes 18, or minus 2, you remove 1 0, you get a 2 into 10 to the power of 17. Always remember, everybody, so whenever they ask you the order of magnitude, this should be a unity. It should not be a power of tens, it should not be hundreds, it should not be a decimal point, but it should be a unit value. So when you come to a unit value, we can notice that it's 10 to the power of 17. So option B is the right answer. So, and imagine the density for water, it is 10 to the power of 3. For water, the density of water is 10 to the power of 3 order. For nuclear, it is 10 to the power of 17. Imagine, it's so dense. It's completely dense. Okay. Am I clear? Am I clear, students? Okay. Okay. So okay. So we'll end with one question, and the remaining questions we will solve accordingly. So which question shall we solve now? Uh, okay, we'll solve two more questions. This is again a simple question here. Okay, so radium is a radioactive substance having half-life of 4 days. So this radium has a half-life of 4 days. Okay, find the probability that a nucleus undergoes decay after two half-lives. Okay, clear. Good. Okay, Radhika, good. So now what's going to happen is, so initially imagine there are 100 nuclei. There are 100 nuclei with me. Okay, so this 100 nuclei will become 50 nuclei, then they become 25 nuclei after two half-lives. One half-life they become 50, after two half-lives they become 25. So now they want us to find what is the probability that a nucleus has undergone two half-lives. Probability, what is probability? Total the number of possibilities divided by total number of possibilities, right? So after two half lives, you can notice 100 has become 25. So when 100 has become 25, which means that 75 of them have undergone decay. So the available number of sets is 75, and the total number of sets is 100. The total number of initial experiment is 100. So you get 75 by 100, or it is 3 by 4. So 3 by 4 is the answer. Okay, correct, Radhika. Good. Okay, am I clear, everyone? Right. Okay, so I'll just wind it up again. So there was lot of particles, hundreds of particles. After two lives, 100 becomes 50, 50 becomes 25. So total number of particles which have gone decay is 75, and the initially available particle was 100. So probability, number of changes by total set, 75 by 100, 3 by 4. You get option C as the right answer. You get option C as the right answer. Right? Okay. And last question for the day, students. Okay. An alpha particle of energy 5 mega electron volt. It's kinetic energy. It's moving very fast. It is having 5 mega electron volt of energy, and it is scattered through 180-degree by a fixed uranium nuclei. So let me tell you what's happening. So let us draw a big uranium nuclei. Uranium nuclei is very big because it has a lot of particles. It has almost 92 protons and 232 protons plus neutrons. So it's very big. And there was a small alpha particle. Alpha particle is how much? Helium. It has 2 protons and 2 neutrons. So this was coming with 5 mega electron volt of kinetic energy, and afterwards it is getting scattered backwards by 180 degree. It is rotating back by 180 degree. Yes, just a minute, Radhika, I'll come back to that. So, sir, can I know which chapter is going on? So, Aditi, we are like trying to discuss the modern physics, like the dual nature, atomic physics, and nuclear physics. We are going to discuss all those things right now. If you have any chapters which you want to be, which you want me to revise, we'll do that in the next class. Okay, not all a problem. You can give me a chapter. Anyone of you can give me any chapter. We'll discuss that in the next class. Okay, impact parameter under perpendicular distance or just scattering. So this is impact parameter. I'll tell you. Okay, Radhika. So there was this small nuclei moving with such a good velocity, returns back 180 degree, because this is also positive in charge. This is also positive in charge. Very optics next. Okay, okay. So positive repel. They're getting repelled and they come back. Okay, so now let us apply the energy conservation. Kinetic energy 1 plus potential energy 1 is equal to kinetic energy 2 plus potential energy 2. So this is the energy conservation, right? So you can notice initially when this is very far away, it has kinetic energy of 5 mega electron volt. Since it is very, very far, I can neglect the potential energy. I'll take it as 0 is equal to when imagine this nuclei has reached this particular point. Okay, now it is going from, it is initially it is going towards right, now it is going towards left. Always remember from the kinematics chapter, whenever that there is a direction of, whenever there is change in direction, velocity becomes 0. So therefore kinetic energy also 0 here. Plus, what is the potential energy? They can't touch each other because both of them are positive. They can't touch, they always repel each other. So the distance between these two is written as d. This d is called the closest distance of approach, or the distance of closest approach. And at that distance, potential energy can be written as q1 q2 divided by 4 pi epsilon naught d. So this is the potential energy formula. Okay, so what is the charge? What is the charge of the particle? Charge of the helium nuclei is 2e because it has 2 protons, and charge of the uranium is 92 times e. Okay, because it has 92 protons, and 4 pi epsilon naught is nothing but 9 into 10 to the power of 9. See, all of them are here. Only thing which I don't know is the distance of closest approach. I can solve this now without any problem easily. So let me rearrange this formula for my simplicity. I'll take this 0 and this 0, I'll remove it out. D at the left hand side is equal to 92 into charge of electron, 2 into charge of electron into 9 into 10 to the power of 9 divided by 5 into mega. Mega is 10 to the power of 6 charge of electron into some volts. So this is how I'm going to do. Now I can cancel electron and electron, sorted. So now what I have to do? I'll write E. E is nothing but 1.6 into 10 to the power of minus 19. Okay, 1.6 into 10 to the power of 19. What can I cancel? So 10 to the power of 6 here I'll cancel, and I'll cancel 10 to the power of 6 here. I will left only 10 to the power of 3. Okay, sorted. So what I've left is 92 into 2 into 9 into 10 to the power of minus 16 divided by 5. Okay, so 5 ones are, so 5 ones are 5, approximately 2s are 2 2s are 4. 4 into 90 gives me 400, approximately 400 into 10 to the power of minus 16 is what do I get. Okay, am I clear? Did I make any mistakes? I hope not. Okay, so let us take the 2 zeros. Let us take 2 zeros and cancel 2 zeros. I get approximately 10 to the power of minus 14. So the answer was supposed to be this one, 10 to the power of minus 15. I think I missed a number somewhere. Okay, so if you do it very carefully, very closely, you'll get the answer without any problem. Okay, students, I hope I'm clear here. Okay. So one thing is very sure. Whenever they ask you to find the magnitude, don't worry about the magnitude. You can calculate approximately. You'll get the right answer. Okay. So and let me explain about this distance of closest approach one more time. So which is whenever there's a big nuclei like the uranium nuclei, okay, And when there is a small nuclei, this is also positive in charge, this is also positive in charge. So this nuclei will be coming very close to this, and then suddenly it will take a reverse turn, because they're positive, they repel back, and when they repel back, the minimum distance between these two, right, is called as the closest distance of approach. You can't, if it is having higher kinetic energy, it will go much more closer, but they never touch each other. It's completely impossible. Okay, so then how can I find this the distance of closest approach? By applying conservation of energy. So I'm going to apply conservation of energy at 2 points particularly, one at a very far point here, and one at this point where the velocity is zero. Here the velocity is zero because velocity is a vector quantity, it is going towards right. Now it is returning back. Whenever change of direction happens, velocity is zero here. So here, kinetic energy plus potential energy at one station should be equal to kinetic energy and potential energy in the second situation. Okay, but since velocity is zero here in the second situation, I can take this as zero. And since this is very far away, I can take potential energy to be zero. Therefore, I can equate that kinetic energy half mv square is equal to potential energy k q1 q2 by d, or 4 pi epsilon naught by d. If you know the kinetic energy, if you know the charges, you can find the distance of closed approach very easily. Okay, so direction towards the nucleus, that is r naught. Okay, this distance is the closest distance, Radhika. Okay, and it traces 180-degree path, means it's exactly going back. It's rotating and it's going back. Okay, am I clear? Am I clear, everybody? So good to see most of you here. Okay, thank you for coming here. Okay, so if you have any doubts, you can leave it in the comment box. And okay, so we'll the next chapter will start with reoptics. Okay, so let me see. Tomorrow I might solve some more questions on this, or we'll start reoptics chapter. Okay, so thank you for being here. Thank you everyone. Bye bye. I mean, I'll give 2 minutes for you to clear any doubts. So if you want any information or any doubts, please ask in the chat box. Okay. And Radhika, this is also called as impact parameter. Okay. So this distance of closed. Okay. Imagine nucleus is not exactly opposite, but nucleus is somewhere very far away like this. Okay. Now what will happen? They come towards, but due to positive repulsion, they go back. Right? There is one more nucleus here. This nucleus going in towards right, but again it's going to get reflected back like this because of positive repulsion. So this distance, this perpendicular distance, is usually we call it as impact parameter. Okay, and this also perpendicular. This is also an impact parameter. This is also impact parameter, and this is also impact parameter. So impact parameter is a very simple concept. It is the perpendicular distance between the parent nuclei and the moving nuclei. That's all. The most minimum distance, the perpendicular distance between the stationary nuclei and the moving nuclei, is called as impact parameter. Okay, and impact parameter will be very less if it is moving exactly on the straight line. If both of them are exactly on the straight line, then the impact parameter will be equal to minimum. Right? All clear, students? So today we discussed about a lot of things, right? Any doubts? If no doubts, I'll end the stream. Okay. So we started with activity. Then we understood photoelectric effect. We understood how to create X-rays. We understood Moseley's law, right, and solve some problems on it. And we learned probability. Then how does electron gives us interference pattern? How does the density and volume of nucleus are proportional to each other, right? And how to calculate the order of magnitude of the closest approaching density of uranium nuclei. So this is what we have gone through, and still some more questions are remaining. So I'll see. Okay, maybe tomorrow also I'll solve some questions, and Saturday we'll start with reoptics. Okay. Good. Okay. Angle of deviation of nuclei 90 degree. From nuclei is doesn't make sense. So angle of deviation to become 90 degree, it's very rare, Radhika. As rare as so if you know our scattering experiment, Rutherford scattering experiment. So this was a gold foil alpha particles come, most of them pass through the gold foil without any deviation. Few of them will deviate like this, and very few of them will retrace the path back. So you to get a 90-degree reflection from a nucleus is very, very rare. It's not possible. I mean, it's possible, but it's quite rare. Okay, and it's completely depend. How do we get the parameter? Depends on the size of nuclei and velocity of this moving particle, moving nuclei. Okay. So how to calculate a perpendicular distance? So very simple. So I'll draw a one line here. Okay, this is a center line, and so this for this, if I want, I'm going to draw a tangent here. Okay, I'm going to draw a tangent, and the distance between this center and this is the perpendicular distance b. Okay, so let me tell you one more time. So I'm going to draw one line which is passing to the center of nuclei as my reference point, and there is one more. This is the trajectory of the particle. There was this nuclei coming, and this nuclei deviates and go back like this. Okay. So next, what I'm trying to do, I'm going to take the perpendicular distance from this line to this line. That will be impact parameter b. Okay. Right. Okay. Okay. Thank you guys. Thank you for being here. See you all tomorrow. Take care. Bye bye.